Hello everyone, welcome to the last week of this course, week 12. You see, this week we are going to introduce a very important concept, just the introduction of that concept. And this week can be you can treat this week as a common link between this course. If you remember, on the very first day, I said this course, the structural analysis 1, is a basic level course, the first course on structural analysis, and there will be several other courses, more advanced courses that you need to take in your curriculum. And this week is essentially a common link between this course and the advanced level course. This is the transition where with the knowledge whatever we have gained in this course, structural analysis 1, can be used to derive more sophisticated method for analysis of structure, that is your advanced structure analysis in subsequent semester. You see, all the methods that you have learned so far, all the methods. Now, up to week 11, we introduced many methods. We have solved several examples. Now, from this week onwards, what you do is you need to look at whatever we have learned so far as a concept, not as a method. Okay. By saying so, what I actually meant is, you see, all those methods that we have discussed so far are developed 100, 150 years back when there was no computer. Everything had to be done manually, and that's why the method had to be very simple. The calculation method should be such that calculations are easier. But you know, now hardly if you go to industry and all practical purposes, the method that we have learned so far, hardly they are used. Because there are more sophisticated methods developed over the years, and those methods are used in industry. But what is important, what we can take from the first 11 week of this course is the concept that we learned. Moment distribution method we don't use nowadays, but the concept of moment distribution is still being used. The concept of slope deflection, concept of indeterminacy, determinacy, concept of method of section, concept of method of joints, the concept of mechanics that we learned so far while discussing those methods. That concept is still relevant, and those concepts are very essential to learn or to analyze any structure, whether you use any method. Okay, so what is take from the first 11 week of this course is the concept that we learned, various concept related to structural mechanics. Okay, now today we'll just introduce this week is direct stiffness method, and more precisely today's class, which is lecture 57, we'll just introduce the concept and see how this concept can be applied to analysis of truss, and then subsequent lecture we'll also see how this method can be applied to analysis of beams and frames, and then some examples. Okay, if you see, this is the last this is the summary of summary of the displacement method that we have already learned, and what it says is, you have a beam, you have a structure here, and this is true for any structure. Now, the degrees of freedom that we are interested in this structure is 4 degrees of freedom: rotation at B, rotation C, rotation D, and rotation E. So theta B, theta C, theta D, and theta E are the degrees of freedom. But depending on the structure, you can have different other degrees of freedom as well. But in this problem, if we have only 4 degrees of freedom, which are denoted as D1, D2, D3, D4, and then corresponding forces at the corresponding joints at B, C, D, E are F1, F2, F3, F4, which are essentially the total summation of the fixed end moments at a particular joint. Now, so these are the forces at these joints. These are the degrees of freedom at these joints that we are interested in. And then these forces and these degrees of freedoms are related through a matrix which is called stiffness matrix, and the K11, K12, these are the elements of the stiffness matrix. Now to get now K11 is essentially it's the K11 is essentially the relation how the F1 and D1 is related, and similarly K12 gives you how F1 and D2 is related, and similarly K13 gives you F1 how F1 and D3 are related, and so on. Another important thing in this stiffness matrix is this stiffness matrix is symmetric. Symmetric means the off diagonal terms are same. K12 is equal to K21, K13 is equal to K31, and that we have already seen. Now you see, now direct stiffness method is or sometimes it is also called matrix method of structure analysis. Okay, now you see, suppose I have we know how to design we know how to okay, let's give you an example. Suppose I have a circle like this, okay, and if you are asked to determine what is the area of this circle, we know that it is pi r square, where r is the radius of the circle, right. Similarly, if we have a square or a rectangle which is side A and B, what is the area? Area is equal to A into B. We can also determine the perimeter and so on. So for regular structure, for regular shape, we can calculate the area and the perimeter. Now if I give you an arbitrary area, okay. Now if I ask you to find out area of this shape. Now you see, now if we need to bring some analogy, these are the in practice our structures are like this. Structures are like this means the structures are just not one portal frame, or structure is just not a cantilever beam or a simply supported beam. A structure is essentially a collection of many beams, many columns with different boundary conditions, different shapes, different sizes, okay, and oriented in 3 dimension. There is no symmetry, okay. They may deform arbitrarily in any direction. So structures are very complicated in real life, okay. So but all the examples that we have done so far, or probably in this class also will be in this week also will be the example we will be doing, are all structures are very similar to this kind of problem, where it is very simple, for which applications are very simple, but in real life the structures are actually like this, okay. Now what we do if we have to find out the area of this shape, we don't know any formula for that. One thing we can do that you all, I'm sure you all know this, that we can divide the entire area into smaller cells of regular rectangle or squares like this, okay. And we have done this probably in many times in schools. Now we know the area of each square, and then count how many squares we have. And if the squares, now the boundary squares, we can take half or 25% depending on the how much area is cut by this line. So we can get the number of total square, and then knowing the area of each square, we can get the total area of this this shape. Okay, and similarly, if we now what it tells you, that if you somehow this is your actual problem, okay. Now if you somehow decompose the problem, divide the problem into smaller sub problems, such that every sub problem you have the information, you know the solution. For instance, in this case the actual problem is the entire area, finding the area of this entire loop, and then but which we cannot find out because we don't know the formula for that. And then what we do is we divide the entire problem into smaller sub problems, and sub problems are finding the area of a square. Okay. Now each sub problem we know the result, we know the solution, we have the information. Now and then what we do is we assemble that information to get the solution of the final structure, okay, or in this case solution of the final problem, final system. Now in real life, when we deal with any problem, and believe me, it is not particularly for structural analysis, it is true for any system. Okay, any system, if you see, as an engineer, at the end of the day, you need to find out solution of some real life problem, right? You need to understand the laws of nature and this mimic those laws to find out the solution. And when you actually in real life, when you face a problem, and those problems doesn't come with a tagline that this problem belongs to civil engineering, this problem belongs to mechanical, this problem belongs to aerospace, and so on. The problem comes as a problem, and as an engineer, you have to deal with the problem. Okay, so now most of the time, almost all the time, that you will see when you deal with a problem, generic process, generic methodology that we use is divide the problem into small sub problems, and such that for all sub problems we know the solution, we have some information, and then we assemble those information to get the solution of the entire system. Now, direct stiffness matrix or matrix method of structural analysis is essential. The premise, one premise of this method is this: you divide the entire system into small system, get the information of all the system, and what information that we'll see. Now we get the information of all the system and then assemble them. Now, depending on the problem you are dealing with, as I said, what information, that depends on the what problem you are dealing with. Now, if the problem is structural analysis problem like this, our information is very similar to this. How the forces and displacements are related to each other. Okay, so means if we have a force, this is the force, and then this force is equal to some stiffness K, and this U is the displacement. Okay, and this K is the stiffness. This is called stiffness, and this is displacement or deformation, and this is force. This is force. Okay. Now, if we know this, relation for a given system, given structure, then what you have to do is if we know the stiffness of a structure, then for a given load, applied load on a structure, we can find out what is the deflection of the structure, or for a given displacement, we can find out what would be the corresponding forces caused by this deflection. And if you look at all the methodology that we have learned so far in first 11 week, we actually did the same thing but in a different way. Okay, now the process that will be followed, that concept can be translated in a way that it can be implemented in computer, because most of all real life structure you cannot really do manually. Remember, moment distribution method, you cannot for a beam it is fine, for a portal frame it is fine, but for any real life structure it is very difficult to do all these iterations manually. So you need to, the concept is fine, but that translation of the concept needs to be in a language that can be used, that can be put in a computer code, so that we can analyze these, we can analyze we can analyze the problem that actually we face in real life. Now here the force is equal to stiffness into displacement. These you have learnt again in previous classes as well. But now the thing is, as I said, this concept needs to be translated in a language that can be put in a computational code. Okay. Now, so what we do is let me see this. If we for direct stiffness method, analysis of structure for direct stiffness method, actually we need a separate course. Okay, but idea of this week is not to again give you entire details of this method. Idea is to have a transition between your basic level course and more advanced level course, and this is the transition for that. So here what we'll do is we'll just briefly try to understand the basic concept, and then probably all these implementation issues, there are minor computational issues that probably we need a different courses for that. Okay, now let us today we'll demonstrate this through a problem of truss problem. Just the concept, numerical demonstration we will be doing in the subsequent classes, and the next class we will see the similar concept for beams and frames. Okay, now you see, take a truss, any truss like this. Suppose this truss. Okay, this is again this is a determinate truss, and this is subjected to any load, say P, any load, say P. Okay, and we need to solve this problem. We need to analyze the truss. We need to find out what are the member forces and corresponding displacement. Now, this method that we are going to discuss, that is whether it is determinate structure, indeterminate structure, every cases you can find out. You can apply it. Okay. Now, this is the real system. So, this system is this. This system is this. Okay. Now, this cannot be. What we do is we decompose the problem into several sub problems. Okay. Now, we decompose the problem into several sub problems means, let us take, this is one member, this is another member, and this is another member. Okay. So, now we deal with each member separately, writing this relation for each member, and then if you look at this example, this is force, stiffness, displacement. This relation is for the entire beam A, B, C, D, E. Okay. Now, what we are going to do is, instead of writing this equation for the entire beam, first we divide the beam into small beam, and similar thing we did in slope deflection method as well. We treated each span as fixed span, if you remember. Now, and then write this relation for each member, okay, here in this member, and then assemble this relation of all the members to get the similar expression, force is equal to stiffness into displacement, similar force displacement relation for the entire structure. Okay. So, we divide it into smaller parts like this, and then write the force displacement relation of these several parts, and then assemble them to get the force displacement relation of the entire part. Okay. Now, what we do is, why it is okay. Now, let's see how it is to be, how it can be done. Okay. Now, take any truss member. Okay, and we already know that truss members are two force members. Either they are subjected to compression or they are subjected to tension. So, either it is a force is like this, a force is like this, or member is this, a force is like this. Okay, and as per our sign convention, and this is tension, this is tension, and this is compression. These are sign convention. So, any truss member. Now, you see, now if you remember, okay, now since this member, these forces are along the axis of the truss, they are either compression or tension. Now, what happened? This force will cause deformation in this truss member, but that deformation will be always in axial direction. So, either for this will cause elongation of the truss, the elongation of this truss member in this direction, and this will cause reduction of length in the truss member in this direction. So, either these members, whatever deformation takes place in this member, that deformation is always axial deformation. Either the deformation causes increase in length of the truss, or truss member, and causes decrease in the length of the truss. So, deformation always in this direction. Okay. Now, let us find out, now suppose that deformation is, suppose this in this member is this is point number 1 or joint number 1, we say this is joint number 1 and this is joint number 2, okay, or this is joint number 1 and this is joint number 2, okay. Now, we take tension as positive and compression as negative, okay. Now, if you remember the Hooke's law said that how the stress and strain are related. We know that sigma is equal to Young's modulus into strain. Okay. Now, if suppose the cross section area of these trusses, this truss member is A, cross section is A, and suppose this truss is subjected to a force called F. Okay. And again, suppose this Young's modulus of this truss member is E. Okay. So, cross sectional area is A, Young's modulus is E, and this truss member is subjected to a force F. That force could be compression, that force could be tension, but these forces is along the longitudinal direction of the truss member. And suppose, okay, let us okay, ANE, suppose this is subjected to a force F, okay, and the properties of the truss member is area is A and Young's modulus E. Now, when it is subjected to a force F, suppose it causes, the force causes displacement U, displacement is U. Again, that displacement is in this direction, either it is in the longitudinal direction. Okay. Now, let us find out how these all parameters, the area, Young's modulus, force and displacement, how these parameters are related to each other, and that relation we get from Hooke's law this. Okay. Now, so sigma is equal to stress, sigma is equal to force by area. Okay. Now, you can put a star mark here. Okay. Star mark here. I am just crudely defining stress as force by area, but as you take courses on continuum mechanics and solid mechanics, many of you might have already taken it, you will see there are different measures of stress, okay, and that is not the that may not be the most it is not the better way we define stress, but for the time being in this context, this definition is absolutely fine for us. Okay. Okay. Now, the sigma can be represented by F by A is equal to Young's modulus is E, and then strain will be displaced. Okay. Let's another important thing. Suppose length of this truss member is L. Okay. Initial length of the truss member is L. Now, so therefore, what will be the strain? Strain is defined as elongation by initial length U by L. Again, there also you can put a star here. There are different measures of strain. Okay, and you will definitely see all different measures of strain in solid mechanics and continuum mechanics course. But again, for the time being, to demonstrate the theory concept, this definition is absolutely fine for us. Okay. Now, if we have this, then next let us write out what is U then. So, this directly comes from Hooke's law. Now, from that we can write U is equal to we have L by A into E into F, okay, and another thing we have F is equal to AE by L into U. Two relations are okay. Now, you see this was the relation we had, that force is equal to stiffness into displacement. You see here also we have the similar thing, force is equal to something into displacement, and this something is essentially the stiffness. Okay. Now, but again this stiffness is associated with only for truss member, this member, where your member forces are only axial and they are subjected to only axial deformation. Okay. But the value, the expression for stiffness for different forces and different kind of degrees of freedom are different, that we will see subsequently. But for axial deformation and axial force causes axial deformation, the stiffness is this. Okay. So, this relation is equal to essentially force in force is equal to stiffness into displacement. Another reason, again I wrote this expression as well. This expression I wrote because here the displacement is equal to inverse of stiffness into force. And if you recall, we discussed in the force method, while discussing force method and displacement method, we say that inverse of the stiffness is equal to flexibility. So it tells that your displacement is equal to flexibility into force. Okay, but we don't need this expression right now. So this is how the force and displacements are related for a truss member. Okay. Now here we introduce a very important concept of local coordinate and global coordinate. Now local coordinate and global coordinates are like this. You see, when we write these expression we assume the forces are in this direction and displacements are also in this direction. But in actual structure, suppose this is the structure, this is the actual truss, if you recall. Now if we are interested in displacement in these directions, we want displacement in, what is the displacement in this direction, what is the displacement in this direction, means if it is my x coordinate and this is y coordinate. So we want what is the displacement in the x direction. Take any joint here, what will the corresponding what is the displacement at joint in x direction and what is the displacement of that joint in y direction. Okay. But these displacements, when you write this displacement u, but deformation u, that deformation is not in x and y with respect to that coordinate system. This is along this deformation, and this is the local coordinate system, and local coordinate system we defined like this. Okay. We define local coordinate system like this. For instance, in this case, your local coordinate system is this is x, say x, and this is y. And in order to differentiate between the global coordinate system and the local coordinate system, let us write is x dash y dash. Okay. So x dash y dash, x dash is along the length of the truss, and which the origin of this coordinate system is at point 1, and y dash is this, and this is local coordinate system, whereas the global coordinate system is like this. This is x and this is y. Okay. So if the truss is like this, this is my global coordinate system. For this member, local coordinate system is this. Again, if you take for this member, say this member is oriented like this, and for this member, suppose this is 1, this is 2, and then we have global coordinate, local coordinate system is this is x dash and this is y dash. Okay. Similarly, for this member, local coordinates, the member is oriented like this, and suppose this is 1 and this is 2, there is nothing that you have to take always this as 1 and this as 2, you can take this as 1, this as 2 as well. In that case, your local coordinate system origin will become here. Okay. So this becomes like this, this becomes your global coordinate system, local coordinate system. This is x dash and this is y dash. Okay. These become local coordinate system, but global coordinate system always remains same. So when we write this relation can be written for this member, this member, this member, this member. When we write this relation is always with respect to the local coordinate system, because u is essentially the deformation in axial deformation. U essentially the axial deformation. But if you remember the methodology is you divide the problem into smaller part, smaller subsystem, and then assemble them. When you divide into smaller subsystem, for each subsystem the equation is written with respect to their local coordinate system. Once you have all the information, once you have the information of all the system with respect to their corresponding local coordinate system, what we need to do is we need to assemble them. But when we assemble them, we need to transfer all this information to global coordinate and then assemble them. Okay. So this is a very important step. We get this relation, first stiffness matrix. We have not yet defined the stiffness matrix yet. We have just defined how the force and displacement can be related. Now we are going to write this expression now this expression, force is equal to K into U for each member with respect to local coordinate system, and then we will see how this equation can be transferred from local to global coordinate system, and then we have to finally assemble them. Okay. Now let us find out quickly what is the now suppose you apply a force like this. Suppose U1 okay, suppose U1 dash and U2 dash, U1 dash and U2 dash are the displacement deformation at point number 1 and point number 2. Okay. U1 dash is the deformation in this direction and U2 dash in the deformation is this direction. Okay. And similarly corresponding forces are P1 dash and P2 dash. They are all written in dash because it is with respect to global with respect to local coordinate system. Okay. Now the member is now only subjected to E1 and E1 and P1. Okay. Now this is the member. Okay, if you remember, this is joint number 1, this is joint number 2, and suppose this member is subjected to displacement E1 and also force P1, and this end is fixed. This end is fixed means there is no deformation here. Okay. Now when you apply a force, when you apply a displacement here, and or when you apply a force here, say it is say force P, if you apply a force P, P1 here, suppose this force is P1, suppose this force is P1 dash, then this P1 dash and E1 dash is related as P1 dash is equal to AE by L into E1 dash. Okay, into E1 dash. This is how just now we defined. Okay. Now you see P1 dash, if you apply a load P1 dash at this point, there will be a reaction at this point, isn't it? And that reaction is, corresponding reaction is, suppose this reaction is P2 dash. Okay. Now, so P2 dash will be minus P1 dash to maintain the equilibrium. So this P2 dash will be P2 dash will be then minus AE by L into E1 dash, isn't it? So you try to understand this. Actually what we are going to do is, we have a member like this where we have displacement at this point and this point both, but we are considering first deformation only at A1, only at point 1, and then see how we have the displacement and force relation, and then similarly we will do keeping point 1 fixed and allowing only point 2 to deform. Okay. So similarly we have take this. So this is fixed, and then we have similarly we have deformation. This will be U2 deformation, and corresponding load will be P2 and then P2 dash, and due to P2 dash the reaction here will be P1 dash. So then they will be related as P2 dash, similarly AE by L into U2 dash, and which will cause reaction P1 dash, which is minus P2, will be minus AE by L into E1 what is called this is U2 dash. Okay, this is U2 dash. Okay. Now you see okay, let's write this as different name. If we can give this as what name can we give? Okay, this P2 and this P2 are not same. That's what. Okay, let's P2 double dash. This is P2 P1 double dash. This is fine, absolutely. Okay. So now this is due to the displacement at E1, displacement at 1, and this is due to displacement at 2. So this is the force P1 dash applying and corresponding displacement at E1 dash, and then on the other hand your reaction will be minus P1 dash, which is equal to this. Now in this case P2 dash force is applying, P2 double dash force is applying here, corresponding displacement is U2 dash, and the relation is this. And then what happened, now this will cause a reaction at this end, and that reaction will be P1 dash, which is P1 double dash, which is negative of this, because they are opposite in direction. To maintain the equilibrium, this will be this. Okay. Now so this is when your displacement allowed at A1, and this is when your displacement allowed at 2. Now when displacements are allowed at both the ends, then what happened? The total forces at 1 will be this plus this, this plus this, and total force at 2 will be this plus this, isn't it? So suppose they are Q1, so Q1 dash and Q2 dash, suppose the total force at 1 at point number 1 and Q2 at the point number 2. So Q1 will be this plus this plus this, and Q2 dash will be this plus this. So we can write Q1 dash is equal to AE by L U1 dash minus AE by L U2 dash. Similarly, Q2 dash will be AE by L minus U2 dash, and then plus AE by L U1 dash. Okay. Now if we write that in a matrix form, what we have is, we have this Q1 dash Q2 dash is equal to AE by L, if we can take common, AE by L, this 1 minus 1 minus 1 1 U1 dash and U2 dash. Okay. So this is the force at point number 1, node number 1, point number 2, and this is displacement at point number 1, displacement at point number 2. Now how these are related to each other, and this relation is exclusively for this member. Okay. Now this member has 2 joints, and this member has 2 degrees of freedom in local coordinate system, remember, and these 2 degrees of freedom is displacement at this point and displacement at this point, axial deformation, and these are degrees are related to this hazard. This is called, so this is stiffness, this is stiffness. Now this stiffness is called member stiffness matrix, member stiffness. This is called member stiffness, and similarly you can get the stiffness of each member separately. Okay. So you have this member, we have determined the stiffness of this member relation, we can have similar relation for this, similar relation for this, but only difference will be your definition of displacement and the forces will be different, because those forces and displacements are defined at a particular joint, and the joints are different for different members. So we have member stiffness relation for each member separately. So we have the member stiffness matrix. Sometimes this member stiffness matrix is also denoted as small ke. Ke for element, I am not using the term element, because you see there is again in subsequent semester will be another course on finite element method, which is a more refined version of this direct stiffness method, and there these are the terms are used there. Each here we are saying that you decompose the entire structure into small substructure. There we say you decompose the entire system into small interstructure into small element. Okay, but let's not use the term element right now. So this is sometimes used as Ke. Now this is called local stiffness matrix or member stiffness matrix. Okay, what we do about this stiffness matrix, we have a stiffness relation for this similar stiffness relation for all the members, but we cannot assemble them, we cannot add them as it is, because we have to transfer them on a same plane with respect to same coordinate system, then only algebraic all this addition and subtraction can take place. So now we will see how this stiffness matrix can be transferred to its global coordinate system. Okay, steps will be clear if we actually solve some examples. Okay, now quickly, now suppose this is the member, okay, and this is your x1, this is point number 1 and this is point number 2, this is point number 1, point number 2, and this is E1, this is E1 dash, and this is here it is U2 dash, okay, and this direction is x1 dash and this direction is y1 dash, okay. So, this is our local system. Now, similarly the global system, corresponding global system will be like this. This is U1 and say it is V1, this is U2 and this is V2, okay, and suppose this angle is theta, this angle is theta. Okay. Now, what we have to transfer? We have to write this E1 dash and U2 dash in terms of E1, U2, E1, U2, V1, V2. Okay. And if this angle is theta, then we can easily write that E1 dash is equal to E1 cos theta plus V1 sin theta, and that you can this thing you can check easily. And I am just writing the final expression cos theta minus plus V2 sin theta, okay. And if you write that in a matrix form, then you have U1 dash U2 dash is equal to cos theta then sin theta 0 0 and then 0 0 cos theta and sin theta, and then you can write this as U1 V1 and U2 and V2, okay. So, same thing written in this way, and suppose lambda x is cos theta and lambda y is equal to sin theta, okay. So, next time onwards we won't write cos theta x cos theta, we will instead of cos theta we will write lambda x, and sin theta we will write lambda y, okay. Now, okay. Now, next what we can do is, so we can write that U1 dash U2 dash in terms of that is equal to lambda x lambda y 0 0 0 0 lambda x lambda y, and then this is U1 V1 U2 and V2, okay. Now, next thing what we have to do, next thing we need to suppose this is T, this expression is written as T. Now, similarly I leave it to you. What we can do is, now here we transferred what? Here we transferred only the displacement, okay. Similarly, we can transfer forces as well. Forces means again we have the same thing. It is joint number 1, this is joint number 2, where we have force, it is P2, this is P1, and it is in local coordinate system P1 dash, this is Q1 dash and this is Q2 dash, and in actual coordinate system we have, suppose this is, we have force like this. Suppose this is P1, P2, P3, P4. Suppose this is P1 and then this is P2, and then this is P2 and then this is P3 and this is P4. Okay. Now, what we have to do is we have to similarly we have to, instead of here it was U2 V2 all this, and instead of that here we have P1 P2 P3 P4. What we have to do is we have to just write P1 P2 P3 P4 in terms of Q1 dash and Q2 dash, and if you do that, I am not writing the final expression, I am writing just the final expression. I leave it to you. You have P1 P2 P3 and P4 this entire thing will be equal to, it is the transfer is same way 0, then sin theta 0, 0, cos theta 0, sin theta, okay. Or we can write this as well, P1, P2, P3, P4 is equal to, and here we have Q1 dash and Q2 dash, okay. And now same thing we can write, substituting cos theta as lambda x 0, then lambda y 0, 0 lambda x and 0 lambda y, 0 lambda y, and this is Q1 dash and Q2 dash, okay. And if you compare this with this expression, then it is essentially T dash. So, this is T dash, okay. Now, we have a relation between U1 displacement, local coordinate displacement and global coordinate displacement. We have a relation between global coordinate load vector load and the local coordinate load. And in addition to that, we know the relation between, we also know this relation here, we also know this relation, okay, this relation. So, what we can do is now, so we also know Q1 dash, Q2 dash, that is equal to K, which is your element stiffness matrix Ke into U1 dash and U2 dash. What we have to do is, now this U1 dash U2 dash is replaced by this, and this Q1 dash and Q2 dash that is replaced by this. If we do that, or we can do is in this expression, this Q1 dash Q2 dash is replaced by this, and then this U1 dash U2 dash is replaced by this, and if we do that, and what we get is, we get P1, P2, P3 and P4, which is your load vector, that is equal to T, which is the transformation, T transpose into Ke, which is the element stiffness matrix, and finally, and then we get T, and this becomes U1, U2, U3 and U4. Okay. And you see what is the size of T transpose? Size of T transpose is 4 cross 2, and this is 2 cross 2, and this is 2 cross 4. So, resultant of this will be 4 cross 4, and this is essentially K. Global stiffness, it is essentially stiffness matrix, element stiffness matrix written with respect to global coordinate system. Why I am saying it is written with respect to global coordinate system? Because this stiffness matrix relates global load vector with global displacement, whereas this stiffness matrix relate local load vector and the local deformation. Okay. So, if you write that finally, if this is the element stiffness matrix written in global coordinate system, and if you substitute T by this and Ke by we have already determined what is the value of expression of Ke, then we final expression of K we get, which is the global stiffness, which is the element stiffness matrix written in global form, will be lambda x square. Lambda x is equal to cos theta, lambda x, lambda y, and then minus lambda x square. You can please verify this, lambda x and lambda y, and then this is lambda x, lambda y square minus lambda x, lambda y, and then minus lambda y square. This is minus lambda square minus lambda x, lambda y, lambda x square, and then lambda x, lambda y, and the final row is minus lambda x, lambda y, minus lambda y square, then lambda x, lambda y, and lambda y square. You see, this matrix is symmetric. Okay. and of course we have another AE by L term. Okay. So, once you know what is the properties of this member, and this, in order to get this we only needed the orientation of this, because lambda x we only needed is the orientation, right. If we see this, if we see this, we only needed the orientation of this member, okay, this angle theta. Okay. Now, so if we know the property and the orientation of this, we can get the element stiffness matrix for the member with respect to global coordinate system. How to assemble them, all the element stiffness matrix, that we will see when we actually solve some problem. So, what we have learned so far: how to determine element stiffness matrix for truss member, and similarly we can determine the element stiffness matrix for other members as well, and then we need to assemble them to get the solution, and then subsequently to get the solution, and assembling and all we will discuss when we actually solve some problems. Okay, these are very brief, I mean a very brief introduction to the analysis of truss using direct stiffness matrix, but as I said, direct stiffness matrix is essentially a new course, it is a separate course altogether. Idea of whatever we have been discussing in this week is just a transition, just to take you whatever we have learnt in the first 11th week with that information to prepare yourself for the next level course, which is advanced structural analysis course. Okay. Next day what we do is, next day we will similarly derive stiffness matrices for beams and frames, and then we'll subsequent day lectures we'll see how to actually use them for solving different structures. Okay. See you next class. Thank you.